So in a previous lecture, we talked about how we should focus on particles moving in one dimension as the simplest way of starting our study of mechanics. And as you know, we're going to be focused on kinematics at this point, which describes the motion. That's what kinematics is for. So what we're talking about now is how would you describe motion? What kind of questions should you be asking if you want to describe the motion of an object? Okay, let's look at an example. Suppose you're driving towards PCC, but you're getting a little bit late. So your classmate would call you asking where you are. And let's see, I have a map here, assuming that you're driving from the east. You are somewhere here. Let me draw it for you. You're somewhere here. This is San Gabriel Boulevard. That's north and south direction. North and south direction. And then you have Colorado. You have Colorado, which is horizontal, east-west, that is. So your classmate wonders where you are, okay? Because you're getting late, so they ask you, where are you? You say, oh, I am on Colorado Boulevard, right? I'm on Colorado Boulevard. This is Colorado. I'm driving towards PCC. This is PCC, by the way. PCC is right here, okay? And exactly where I am. I am one block east of the San Gabriel Boulevard intersection. So here's the intersection. I'm gonna use a different color now. Here's the intersection between Colorado and San Gabriel, right here. That's the intersection. I am one block east of that, so I am here. So this is how you describe your position to your classmate. Basically, you have, you're telling them you are driving on Colorado. That is the axis along which you're moving. So it's a one-dimensional motion, right? Indicated by this red line here. And you have a reference, and the reference is intersection between Colorado and San Gabriel, right here. That's your reference. And using that reference, you can position yourself. You say, I am one block east of that. Of course, you know, it's approximate because you don't know exactly how long one block is. If you can be more specific, if you can say, oh, I'm about 20 meters east of. So you're looking at your car right here, okay? Your car right here. And here's the intersection. I'm trying to get this pen to work. Here's the intersection. This is your car. This distance is 20 meters. And that's sort of pinpoints where you are. See, so in order to establish your position, uniquely describe your position in a one-dimensional motion, you first have to specify the line on which you move. In this case, is Colorado Boulevard. And you also then have to choose a reference point. In this case, it's the intersection of Colorado and San Gabriel. And you indicate your position relative to that reference point on the axis of motion. So you're saying, I am 20 meters east of that intersection. Right? So this is how we describe motion in general in one dimension. We choose a coordinate system, which is usually we call it x-axis, with a reference point, which is called the origin, 0, right? And typically we choose a coordinate system by convention, choosing e squared as positive. So we usually choose e squared as positive. You don't have to, okay? But if we follow this convention here, then if we call this the origin of the coordinate system, the intersection, you are 20 meters east of the intersection. And you know, going east is positive because the way we describe the positive direction, east, and here's west, right? Then you can say your position is positive 20 meters. Okay? This is a number on the axis, on the x-axis, which indicates your position. So this is how we specify the position. One number is enough to specify the position of a particle moving along the x-axis. And that is the distance between the particle and the reference point. It can be plus or minus depending on which side of the origin this point is located. If you are here, for example, and that distance between here and there, if that distance is 200 meters, then your position would be negative 200 meters because positive direction is considered this way, right? It's considered this way. So you will be negative 200 meters. So a single number X describes where you are, right? And that's called a position. Now, if the position changes, then we have what's called a displacement. Okay, so what is a displacement? A displacement is a change in position, delta X. You start with X initial, we end up with X final. The difference is called delta X, displacement. Okay, so again, displacement is a position, it's a change in position. Now, given the first question that's being answered, where are you or where is it? The next question is, so how fast are you moving? You're already late. Are you moving fast or moving slowly? You say, oh, I am driving at 30 miles per hour. Okay, that is how fast you're moving. That is your velocity. So that's the next piece of information. Now, velocity also has a sense of direction. In this case, it's implied that you're going, because you're going towards PCC from the east, so you're driving west. And in the symbol, in the convention of direction that we use, since you're going west, that's against the positive direction, which is east by convention. So the velocity would be negative 30 miles per hour. That negative, there's nothing with negative sign. The negative only means you are going against our choice of positive direction, which is east. Okay, so that is the next thing you want to know, how fast you're moving, the velocity. And again, velocity has an implied direction, but in this case, the direction is very clear. The direction is west, and that's indicated by a negative sign because going east is considered positive, going west is considered negative. And these are the only two possible directions if you're going to be driving along Colorado, because it's an east-west road, so you can only drive either east or west, no third possibility. And therefore, we don't have to use any vectors to indicate the direction of motion. Okay, east is positive, west is negative, and that's it. And if you want to study further about the state of motion, then you can ask another question, that is, are you picking up any speed? Is the traffic getting any better? Are you going faster or going slower? Then this has to do with how the velocity changes, okay? And that is known as what? As acceleration. So we have three important quantities: position, velocity, and acceleration. And they can all be written down as a formula and also expressed on a graphical sheet. You can plot X versus time and V versus time. You can get a graphical representation of these quantities. Now, so from X, how does one get velocity? How does one get velocity? Well, if I plot X as a function of time, you can see here X as a function of time, you can see how we can find velocity, okay? Let's say at t equal to 1 second, you're right here, okay? You are right here. This point, this is where you are. You are at 5 meters, positive 5 meters, let's say, right? So you're 5 meters on the positive side of the x-axis from the origin. And then 1.2 seconds later, let's say this is 1.2 seconds, okay? You have arrived at a new point, which is 6 meters away from the origin. So you've moved by delta x, which is equal to what? Final position minus initial position, that's 6 minus 5, and that is 1 meter. Whereas the time interval for that to happen, delta t, is equal to what? 1.2 minus 1, and that is 0.2 seconds. So you move by a meter in 0.2 seconds. How fast did you move during that 0.2 second interval? That is the velocity. So velocity is defined as the rate at which the position changes, okay? And that is, in this case, 1 meter over 0.2 seconds, and that is 5 meters per second. That's how fast you're moving between 1 second and 1.2 seconds. But what you're getting here is what's called average velocity between t equal to 1 second and t equal to 1.2 seconds. During that time, even though the time interval is pretty short, 0.2 seconds, it is still possible for you to change your velocity, right? What we're getting is only the average velocity. So what if you want to know precisely how fast you're moving at the 1 second moment? So t equal to 1 second, you were right here. You're right here. How fast you're moving at this moment? Well, you're going to have to shorten delta t, because with a shorter delta t, there is less of a chance for your car to accelerate or decelerate, right? So the average velocity will get closer to the instantaneous velocity. So instead of 0.2 seconds, you can use say 0.02 seconds. If that is even that is not too, it's not short enough, you can use 0.002 seconds and so on. And if you keep on decreasing delta t, then delta x will also decrease, but the ratio of delta t over delta x now becomes, will approach a constant. And that constant will approach a limit, and that limit is your velocity at precisely t equal to 1 second. So this is the average velocity, okay, but the instantaneous velocity at that moment, you're gonna have to take the limit of delta t approaching 0. Again, you take delta t approach 0 because you want to look at such a tiny interval, time interval, so that during that time interval, there is no chance for the velocity to change. So the average velocity during that time infinitesimal with small time interval equals the instantaneous velocity. Because again, the velocity doesn't have a chance to change yet. The time is too short, okay? But as you know, mathematically, if you take that limit, delta x over delta t with delta t approaching 0, what you're getting is the first derivative of x with respect to time, so dx over dt. So dt is really the infinitesimal amount of delta t, okay? So you see, you start with x as a function of time. If you know that function as a function of time, you just take a derivative, dx over dt, you get what? You get velocity, okay? Now, similarly, you can look at how velocity changes, and that is what's called acceleration, right? So suppose I draw a picture, draw a graph of how v changes as a function of time. Let's say initially you start from 0, at t equal to 0, you start with 0 velocity, but you can see here the velocity increases, okay? The velocity increases between t equal to 0 and t equal to 1 second. It went from 0 meters per second to 5 meters per second. You can see from here, 5 meters per second. Okay, 5 meters per second at t equal to 1 second. So how fast did the velocity change during that 1 second interval? Well, instead of delta x over delta t, I'm gonna have to look at how the velocity changes. So delta v is, in this case, v final minus v initial, and that is, in our case, is 1 meters per second, because it went from 0 to 1 meter per second. And the time interval is 1 second. I'm sorry, delta v is 5 meters per second, went from 0 to 5, right? So it's 5 meters per second, but delta t is 1 second. And therefore, the average rate at which the velocity changes during the first 1 second time interval is 5 meters per second divided by 1 second. And interestingly enough, it's got a funny unit. It's 5 meters per second squared, right? Per second squared. You can also read it as 5 meters per second, the same as 5 meters per second squared. What does that mean, meters per second squared? Okay, this 5 meters per second squared means that during the first 1 second of motion, the velocity changes at a rate of 5 meters per second every second. And that is, the velocity changes by as much as 5 meters per second with every passing second. That's what it means. Okay, this is what's called the average acceleration between t equal to 0 and t equal to 1 second. And once again, if you're looking for the instantaneous acceleration, you cannot assume, that during this 1 second time interval, the velocity didn't change. The acceleration didn't change. If it didn't change, you will get a straight line, and that's pretty close to a straight line as we draw, but it doesn't have to be the case. The acceleration can be different during different moments of that 1 second interval. Again, the strategy, if you want to get instantaneous acceleration, is to limit delta t, make it as small as possible, make it so small that during such an incredibly short time duration delta t, there's just no time for the acceleration to change. Okay, so the average acceleration during this very incredibly small time interval equals to the instantaneous value of the acceleration. So we're going to take the limit of delta t approaching 0, just like we did before, delta v over delta t. And that, as you know, is dv over dt, right? Again, the definition of limits. But remember, v itself is dx over dt. As you can see here, v itself is dx over dt. So therefore, I can also write this as ddt of dx over dt. And as you know, this is the second derivative of x with respect to time. So we went from x, we take a derivative, we got v. And then we went from v to a by taking another derivative. So went from first to the second derivative. You can see here how you go from x to v to a by taking derivative ddt, ddt. Now, of course, you can go backwards. That is called antiderivative, otherwise known as integral. So you can go backwards. You have to integrate over time. You have to integrate over time. Okay, so we say v dv equals a dt, right? Because a equals dv dt, and then we integrate both sides. From, let's say we start from t equal to 0. T equal to 0 to the current moment t. In the meantime, v changes from initial value, v initial, which is how fast it's moving at t equal to 0, to the current value of v. Now, if you integrate, if you work out the integral of both sides, the left-hand side is complete integral, so it's just v minus v initial. The right-hand side, I don't know what a is. A could be a constant. It doesn't have to be a constant. So if you don't have any further information, you have to leave it as is, a dt. So you see, when I go from a back to v, I have to integrate. And in doing so, I am introducing a constant here. Okay? That is the initial velocity. When you differentiate both sides, this constant will disappear. Right? But in order to find the velocity at any moment from acceleration, you have to tell me something. You have to tell me what happens at initial moment. That's called initial condition. Similarly, you can go from v to x. And the way you do that is you're going to start from, just like here, instead of dv equals a dt, you're going to start with dx equals v dt. Right? And you integrate both sides, just like we did here. And from t equal to 0 to the current moment, the value of the position went from x initial to the current value x. So you have x minus x initial equals to the integral of v dt. Now we have to stop here because I don't know how v changes, whether it's a constant, whether it changes, whatever. If there's any acceleration and v is not a constant, I have to know what that function is before I can actually complete the integral. But once again, you're going to introduce a new initial value, x initial here, before you can complete, before you can uniquely determine what x is, right? So this is mathematically how I would go from the position to the velocity to the acceleration. And again, please be careful about the difference between instantaneous and average values of the acceleration and velocity. Now, one of the more important techniques when it comes to studying the quantities x, v, and a is to understand how we can draw a diagram of x versus t and v versus t. That is how to represent these quantities graphically. And once you draw a diagram, if you look at a diagram, I should be able to interpret at least qualitatively how the thing moves. Okay, or backwards, if you describe to me how the thing moves, I should be able to draw an x versus t or v versus t curve for you. For example, I have here an example of x versus t. Right, x versus t. Let's look at what happens for these segments, 1, 2, 3, 4, 5, and 6. What happens in segment number 1? Well, here's the t-axis. Here's the t-axis. Here's the t-axis. And so as time progresses between this moment and that moment, X stays the same. See that X stays the same. What does that tell you? It's not even moving, okay? As a matter of fact, you can see why it's not moving because the velocity is dx over dt. The velocity is dx over dt. But dx over dt, if you plot x as a function of time, dx over dt, as you know, the derivative is the slope of the curve. And the slope of the curve is 0 in this case because the curve is flat. It's horizontal, so the slope is 0, and therefore the velocity is 0. It's not moving, okay? It's not moving until this moment, then it starts to move. So it starts to move forward along the positive x direction, so x increases over time, see? X increases over time, right? Between here and there, x increases over time. But it increases at a constant rate. It's a straight line. What does that tell you? The slope of x versus t between here and there is a constant. But the slope of x versus t is what? Is v, because that's dx over dt, that's v. So the velocity stays at the constant. You start from rest, and you start moving at a constant rate, okay? At a constant rate. Now, when you reach this point, it's no longer a straight line, rather it's a curve, and it curves upwards, okay? There is a positive second derivative that curves upwards. What did that tell you? You're still going forward because x keeps on increasing over time. But at the same moment, you also realize that the slope is getting steeper. You have a smaller slope here. You have a smaller slope here, but you have a greater slope there, right? So the slope increases, and slope, as you know, is the velocity. So the velocity is no longer constant, rather it increases. So not only going forward, you're going faster and faster, okay? When you reach this point, what happens next between here and there? Well, you're still going forward because x keeps on increasing, right? X is still increasing, but the slope is getting less, right? The slope here is, hold on. The slope here, let me use a different color now, is this much, but now becomes that much, which is essentially 0. So you're going forward, but at a slower and slower rate, which means you're going forward, but you're slowing down, okay? You're slowing down. And once you reach this point, what's so special about this point? At the very top of the path, right here. What's so special? Well, this is as far as you reached in the x direction. And the local slope is 0, which means what? You're not going any further, okay? You have reached the furthest point along the x-axis, and your velocity is 0 because the slope is 0. You have stopped, and the next thing that happens is that you have now a negative slope, which means what? You're going backwards, because dx dt is negative, means the velocity is negative. Velocity being negative, as you know, means you're going along the negative x-axis. So you've been going forward all the way till this point, and then you start to go backwards, okay? Not only are you starting going backwards, the slope gets steeper and steeper as you see here. So not only are you going backwards, but you're going faster and faster, right? When you reach this point, from this point on, what you're getting is a straight line, which means you're going backward, but at a constant rate, Okay, so this is how you quantitatively describe the motion. So you can see what's important. The slope is important, that's the velocity, and also whether the slope increase or decrease, and that is whether it curves like this or whether it curves like that. It also makes a difference. If the curves like this, that means the second derivative is negative. It's curving downwards. Okay, it means you have a negative acceleration. Okay, here the second derivative is positive. That means you have a positive acceleration. Now, positive acceleration, does that mean you are going faster? Negative acceleration, does that mean you're going slower? Well, that's something you should really think about. A lot of people automatically assume that because you have a positive acceleration, you are going faster. With a negative acceleration, you are going slower. Is that always true? Sometimes it is, right? Is that always true? Well, you have to understand what positive and negative sign really means. As we mentioned earlier, a positive sign and negative sign, they tell the directions apart. There's only two possible directions, right? In one-dimensional motion. One we call positive, the other we call negative. But a positive acceleration only means the direction of the acceleration is along what? Is along the positive x-axis. Okay, that's what positive acceleration means. Does that mean you are speeding up necessarily? Well, no, because it depends on in which direction you are moving. Let's say you are going along the positive direction. Okay, so you're going this way. Velocity is positive. And at the same time, acceleration is also positive, right? So you're going forward and you're being pushed from behind, right? You're being pushed from behind. You see, of course you're going faster, right? But on the other hand, suppose you're going forward. So V is positive, okay? V is positive, you're going forward. You're going forward. But acceleration is negative. The acceleration is negative. So somebody tries to pull you back, you're going to slow down. So here you see, positive acceleration does make you go faster. Negative action does make you go slower. But that is only because you're going along a positive x direction. Okay. What if you are going along the negative x direction? So you're going this way. Okay. I'm gonna. So I'm going to plot a direction of motion which is negative. Okay, there's nothing wrong with a negative direction of motion. It only means the direction of motion is against the positive direction. So you're going, say, you're going east, you're going west. Okay, you're going west, but the acceleration is positive. What does that mean? It means the acceleration is eastward. Okay, so the acceleration is eastward. See, so V goes this way, but A goes this way. So A is positive, B is negative. So you see, you try to go east, somebody tries to pull you west. You try to go west, right, this way. Somebody tries to pull you east. So what happens? Are you speeding up or slowing down? You're slowing down. But guess what? You have a positive acceleration and you're slowing down. So you see, positive acceleration does not always make you go faster, okay? You can also look at a situation where you're going east. You're going east and the acceleration is also east. You're going west. This direction is west. The acceleration is also west. So the velocity is negative. The acceleration is also negative. But guess what? You're going faster, right? You're getting a push from behind. You're going faster westward. So you see, whether or not you are speeding up or slowing down, it's not because the acceleration is positive or negative. No. It has to do with whether V and A are in the same direction or not. And that is whether they have the same sign or not. If V and A are both positive, that means you're going forward and you're being pushed forward, you're going to go faster. If V and A have opposite signs, they have opposite direction. Let's say V is positive, but A is negative, or when V is negative, A is positive, then the situation is very different. It means you're going to slow down. It doesn't matter when A is positive or not. It means as long as A and V are on opposite direction, you are going to slow down. Okay, so be careful about that. All right, now we can take a look at an example. If I plotted V versus T, I already saw what happens with X versus T using this example. Now look at V versus T. Okay, can we qualitatively describe the motion for V versus T? Well, between here and there, what happens? Well, you're moving, okay, because V is not zero. As long as V is not zero, you're moving, but you're moving at a constant rate, uniform motion. Okay, now as you reach this point, and then when you go to between here and there, what happens? Well, is V positive or negative? V is positive. Okay, now V is negative when the curve is below the t-axis. So V is positive, you're still going forward. Okay, look, you're still going forward, even though the slope is negative. The slope of V versus T is not V, it is A. It means the acceleration is negative. Okay, so V is positive, but the acceleration is negative. The slope is negative, right? It means what? You're slowing down. All right, so you're still going forward, but you're slowing down until you reach this point when your velocity is what? Is zero. You have temporarily stopped. And what happens next? What happens next is that you have a stage like this. For this entire time duration, V is negative, which means what? You're going backwards. Okay, you're going backwards, but between this point and that point, what's happening? You're going backwards and going faster and faster because V becomes more and more negative. It's because the acceleration is also negative. Look at the slope. Acceleration is also negative. Both V and A are negatives means you're going faster and faster along the negative x-axis. Okay, this is the moment you reach the fastest speed going backwards. All right. After that, you're still going backwards because V is still negative, but you're going slower. You're going slower and slower and slow until you reach this point right here, where you have temporarily stopped. Okay, after that, V becomes positive. See, V becomes positive. And if this is a straight line, it means you are going forward with a uniform acceleration, pick up a speed at a uniform rate, and you're going in a positive X direction. So that's how you describe the motion qualitatively, right? The same curve, if it's V versus T, the situation is very different when you plot the same shape of curve as X versus T. But the point here I want to make is that given these curves, you should be able to describe the motion qualitatively. Or, like I said, if I told you how the thing moves, whether uniform acceleration or whatever, you should be able to draw V versus T and X versus T qualitatively, right? So this is what we're going to talk about in a second lecture, and that is what kind of quantities do we need to know in order to describe the motion fully? What kind of questions do we ask, right? And it turns out that we need to know X, and then take derivative, get V, take another derivative, get A. You can also go backwards, and then you should know how to plot X versus T and V versus T qualitatively to describe the motion.